Chapter 4, this is the beginning of it, deals with polynomial functions. So we first have to define what we mean by a polynomial function. And we don't have to get too deep into it really because we've been dealing with polynomial functions. All these quadratics that we've been solving, one of the ways we solve them is to graph them as an equation. And they've all been functions. They all pass the vertical line test. Each x it means, and so equation here is on the left, if we write it that way, and the right is the same thing. It's just written with this function notation, and all that function notation means is that this equation, every time you plug in an x, only one number comes out, and that's all it means. Okay, so we've been dealing with them, and all these quadratics were functions, and so they're all quadratic functions, and these are polynomials. Okay, but let's get a little more specific about this idea of polynomials. What we have to do in this chapter is expand beyond the just quadratic and get into x cubes, x to the fourth, etc. So let's first define or decide what makes a polynomial function. I'm going to get rid of this slide. That's going to let me. So we'll ignore that slide at some point. I'm going to jump to this one right here, and we're going to focus on this top little part here. Since we're going to be working with polynomials, we need to first know what the heck a monomial is, because those are the building blocks that make polynomial functions. Now, what we are used to talking about is just terms. First term of an equation, second term, third term, like terms, not like terms, the real part, the real term, the imaginary parts. But terms, when we first learned them, they are defined as just a number. So a number like this 4 right here, that's a term. A variable like this x sitting here, or a product of a number and variable, like this 5 times this x right here. Those are what terms are. But monomials have to do exactly or be exactly the same thing, but they've got this last condition on them that terms do not. And that is the exponents have to be whole numbers. And whole numbers are 0, 1, 2, 3, 4, on and on and on forever. But notice they're all positives. There's no fractions. And so our exponents have to be that in our terms in order for them to qualify as monomials, the building blocks of these polynomials. Okay, so monomials, mono meaning one, you take one of these monomials, you add it to another one, and you get polynomials, many monomials put together. So on the left-hand side of this slide here, I have a bunch of terms listed. And I'm going to go through each one here and explain whether the term is a monomial. Does it qualify? Okay, basically, are the exponents whole numbers? Because if they are, then we have ourselves a monomial. So if we look at this first term here, 5x over 3, we can see that's a 5/3 a number times a variable. And the exponent on the variable, it's x to the, they don't show an exponent, but that's an implied exponent of 1 right there. Okay, so 5x divided by 3 is a monomial. Next one here, let's take a look at that guy. Let's see, this would be the same thing as if you'd like to see the numerical part, the coefficient part. It's the same thing as negative 1/3 times x. The x here has an exponent of 1, and therefore, yeah, that thing is a monomial. Let's get rid of this. There we go. Negative 7x to the 2/3, certainly a number times a variable, and we check the exponent here. That exponent is not one of these whole numbers. And because of that, this would not ever be in one of our polynomials. It is not a monomial because of that exponent there. Not a whole number. Therefore, it's not a monomial. And we'll never have to deal with it in these polynomials. This one right here, I've shown this one because, let's see here, I had this one where the x's were in the numerator, and here I've got the x off to the side. Well, this is the same thing as 8x over 3. Okay, if you think about it, this is 8 over 3 times an x, which is x over 1. When you multiply, you go straight across. So there's the 8x over 3. And if you look at it in that fashion, you can certainly see it's 8/3. There's the number times the variable x, and that x is to the first power. So yeah, that's going to be a monomial. We could see that in one of our equations. This guy right here and this guy right here are closely related to each other. So I'm going to deal with those at the end. So I'm going to look at this guy to see if he qualifies. See, it is a number, root 7, times a variable, x, and it's to a whole number. Yeah, that's got everything. Put that right in there. That root 7 doesn't stop it from being a monomial. Now, these two right here are both not monomials. This one, it's very clear that it's not. This is 5x to the negative 3, and we haven't done a whole lot with negative exponents, but here's what that means. That negative exponent means the reciprocal. It actually means 1 over x to the third, which is 5 over x to the third. So when you have a negative exponent, that really means the x is in the denominator. However, we cannot have in our monomials x's in the denominator because they are really negative exponents. And so negative exponents are not allowed because they are not whole numbers. You say, well, just write it this way. With the x in the denominator, and now it's a positive exponent. But what you'll see is, first of all, when we write these things, we want our x's all in the numerator, which forces the negative exponent. And the second thing is, look at how different these graphs are. If I were to graph y equals x squared, for example, we know we get a parabola. But if I were to graph y equals 1 over x squared, I do not get a parabola. Instead, I get this funky thing that kind of looks like this. It's really strange looking, but it doesn't look at all like a quadratic equation because it's not. Okay, x's in the denominator really imply these negative exponents, and so these things are not monomials. This one, not that one, this one. Just want to grab part of it. Just ungroup that quickly. That guy right there, negative exponent, he cannot be in a polynomial because he is not a monomial. And we can't have variables in the denominator because that would imply a negative exponent as well, like that. Now, we don't really have to worry about those other than the fact that if we see anything like that, we go, oh, that none of this stuff applies to that problem because these polynomials can only be made with monomials. So now we know what monomials are. These just terms that have positive exponents that are whole numbers on them. So how do we get polynomials from that? Well, the monomials, you just take those things, and if you add them together, you get polynomials. Okay, many monomials. So single monomials, we just looked at a bunch of those. Look how easy these are to write now. You go, well, what exponent can you use? Only these nice positive integers. The coefficients, the number next to the variable, it can be anything it wants to be. So those are what monomials look like. And then if we add a couple of monomials together, as long as we can't combine them because they are not like terms, one's an x squared, one's an x to the fifth. Like terms have to have same variable and exponents, so they aren't like terms. And so these two have to just be separated with this plus in here. Okay, and so this is what we call a binomial because it has two terms in it, or two monomials together. Now, this guy right here, a couple things. We usually don't put plus minus. So it would look just like this. I just wrote it that way so you could see that even subtractions are really an addition. Okay, and we want to put these things in standard form when we see them, which means put the highest exponent term first. We'll be talking about these exponents. They're called the degree of the term. And then put your second highest exponent term next. So that'd be our standard form for this binomial. Trinomials, we've seen tons of these things now. Okay, we saw them all as quadratics. 5x squared plus 3x minus 7, that would be a trinomial. But they don't have to be just quadratics. You could have something like 7x to the 54th minus 3x to the 17th plus 5x. Can't combine any of those terms because they all have different exponents, but there's 3 of them. Trinomial, tri meaning 3, bi meaning 2. So 2 monomials is a bi, and 3 monomials is a tri. And then once we get past 3, then we just call them 4-term. I don't want to put a 4 there. Let's do 5x cubed plus 2x squared minus 17x plus 6. That would be a 4-term polynomial. And then after that we go 5-term, 6-term. Okay? You can see I've written this thing in standard form. Okay? And let's talk about this just a little bit. We want to make sure we're all using the same kind of terminology. So here we are, and each of these are terms or monomials. I'm going to be more specific. Etc. And I should write this monomial under each one. I'll just draw arrows there. And then in each of those monomials, we have different parts to it. So this would be your coefficient here. And then obviously we got our variable right there, the x. And then we have our exponent. Now this exponent has another name. It is called the degree of that term. Okay, it's just another way, so we don't have to say exponent 3, we just go degree 3. Now, degree is not always just the highest exponent. Let me explain that real quick. Let's say this is my term or my monomial. This would be 7th degree. That's pretty straightforward. The only time, I got my g in there, the only time you have to do something maybe a little different is if it's something like this, where you had 2 variables in there. In which case, to get its degree, you actually have to add all those exponents. So this would be a 10th degree. Now, for our purposes, we're just going to have single exponents, our variables in there. So it'll just be your highest exponent. Or rather, your exponent will be your degree. Okay, and so each of these terms, they have coefficients and they have a degree. So this is the 2nd degree term. This is the 1st degree term. This is the x to the 0 term. We usually don't show that x to the 0 because anything to the 0 power is equal to 1. So that's just 6 times 1. So we never show the 0 power x. But it is kind of represented there in our imagination. Now, when it's in standard form, we can get a little more specific about it. So here's your leading term, we call it. And the lead term is your highest degree term. And so one of the things we get asked about is what's the leading coefficient? And so the leading coefficient is the coefficient of the leading term, just 5. And we'll see that in this table here coming up. So take a look at this thing. I'll show you quickly what's going on here. So we've got polynomials listed, so you don't have to check if they're polynomials. They are. Okay, they're also in standard form. Now that helps us out a ton because that means the highest degree exponent is always first. If you look at h here, for example, zoom in there so we can see them really good. You can see it goes x cubed, x squared, x to the 1st, and then there's no x's in this last term. X to the 4th, x cubed, x squared, this is that x to the 0 that we don't show. Even if you only have two terms, you still put the highest one first. So this is a 5 for the highest exponent. And because they're in standard form, it makes finding the degree very, very easy. Okay, if they aren't in standard form, you just put them in standard form. We'll cover that in just a moment. So this one, exponent on the x there is just 1, so it's degree 1. Next one, the highest exponent is 2, so this second degree is the highest degree in the polynomial. The degree of this polynomial is 3, degree is 4, degree is 5. Notice how easy it is when they're in standard form. It's just that highest exponent. Now, a little bit of vocabulary. Okay, each of these degrees then gets given a name. So first degree ones we've covered before. Those are the ones that give you lines, and we call them linear. X squareds, we just got done using the quadratic formula, so these are called quadratic if you have an x squared in them. Threes are cubes or cubic. They're called cubes because cubes have 3 dimensions, length, width, and depth. This one's cubic. New word, to the 4th power is called quartic. To the 5th power is called quintic. And to the 6th power is, we get lazy again, sixth degree is how you put. Okay, and so the only new ones really here, I hope, are quartic and quintic. Okay, and even those aren't used super strictly. In other words, rather than calling something 4th degree or quartic, they might just call this 4th degree, just like they do with the 6th degree. Now, leading coefficients, remember that comes from the first term's coefficient. You don't put the x with it, so this first one, the thing with the x, is negative 2/3. Here's our lead coefficient, negative 4. Lead coefficient, let me circle them in red maybe, negative 5. Lead coefficient, let's zoom in there a little bit. Lead coefficient right there is a 2. Lead coefficient right here, they don't show it. They just have a negative x to the 4th, but that's a negative 1. Here, x to the 5th, that's a 1x to the 5th. Can't be 0x to the 5th because 0 would just get rid of the x to the 5th. Here we got 1 for our lead coefficient, and here we got a negative 4. Notice we're taking that sign with it. All right, so that's how we name them by degree. This is how we find their lead coefficient. Last thing we'll do is look at how you name it by degree, and it should say number of terms here. So like this first one, by degree we call it linear. By number of terms, it only has 1 term, so that's called a monomial, the easiest one we have. Second one is quadratic by its degree, x squared. And it's got 1, 2, 3 terms in it, so it's a trinomial. See here, next one it's cubic, and it's got 2 terms. So it's a cubic, and 2 is binomial. 2 monomials. 1, 2, 4 terms in this one. Watch how fancy we get here. Cubic, because it's still cubic, 3rd degree. And then we just call it a polynomial because we're past 3 terms. Next one's a quartic, 4th degree. See how many terms it has. 1, 2, 3, 4 terms, so it gets the name polynomial. Then we got a quintic, just name it by a degree. And, 2 terms. So we'll call it a binomial. And then our very last one here, choose that green, 6th degree, there it is by degree, and it's got 3 terms, so that's a trinomial. So right away when someone goes 6th degree trinomial, I know the first term is an x to the 6th. They tell me the lead coefficient, I know it's negative 4x to the 6th. Okay, it's only got 2 terms. And then you just tell me the second term, or 3 terms, trinomial. And so I just have to know the other 2. Now, these were all in standard form. If it's not in standard form, let's say I've got f of x. Watch me build a big polynomial here, x to the 7th. All that matters is that when I make this, is that all my exponents are nice and positive. Let's make this one a, I don't know, 8. So here I've got a polynomial I've written. Got x to the 7th term and x to the 10th term. So this is degree 7 term, degree 10 term, degree 8 term, constant. We don't say degree 0, we just call it the constant, because it doesn't have any variable with it, so it's the opposite of being variable. Now, this is a function. You don't move stuff left and right. We're just going to use the commutative property of addition, which says if you add two numbers, you can go 2 plus 3, or you can go 3 plus 2. It doesn't matter. And so the same thing applies here. I want the 10th term, or the 10th degree term first. So I just slide him over there. Then I want the next highest degree, which is the 8th degree term. Then I want the next highest, the x to the 7th. And then finally my constant at the end. So you just rearrange it, put it in standard form like that, and now you can see your lead coefficient is negative 2/3. You can see your degree is 10. Right there. And you can see it goes in descending order. Alright, very last thing. So that's how we name them. Want that all on one slide. There you go. And the last thing is, when we graph these things, and we had some graphing assignment just the other day, and maybe you noticed some of the similarities between them, maybe you didn't. Regardless, here's some of the information you should know. First of all, if you got a polynomial function and you graph it, it's always continuous. That's this one right here. Okay, when you're continuous, you can trace a function from beginning to end and never have to lift your pencil. That's what it means to be continuous. It never has a break in it. Whereas this second graph over here, if I start to trace it, I get to this point, I have to pick up my pencil and jump to the other branch. And our our polynomial functions do not do that. They are nice, continuous graphs. Now, I overdrew it here, but let me show you this. This is really kind of neat. This thing looks like a nice continuous parabola, doesn't it? Okay, but boy, if you look really, really close, and I'm going to zoom in here really tight, this thing's got a hole in it right there. So whatever this quadratic function is, it is, or whatever this equation is, it is not a polynomial. In fact, over here I've got the equation, and you can see the numerator does just fine for us. It's x cubed, x squared, that's okay. But see, we got an x in the bottom. And see, we'd have to take this whole thing to the numerator and put it all to a -1 exponent. This thing is not a polynomial. Looks like a polynomial, but it is not continuous. It's got that gap in it. And if I were to trace it, I'd have to pick up my pencil, jump over the hole, and then continue. So graphs can be a little misleading if you don't look at them really close. Alright, so we know that they're going to be continuous when we graph them, and the opposite is true. If you see a continuous graph, good chance it came from a polynomial function many times. Here's another characteristic, though, you're looking for. Is it smooth? Okay, let me show you smooth versus non-smooth. I saw this, this 7th degree polynomial we had to graph yesterday, and I saw people draw this in, and that's a nice graph. It's nice and smooth and continuous. And I saw other people draw theirs like this, and they said, it might have a dip in it, and they've drawn it up like that, and said, something like that. Again, the right end's going the correct way, left end's going down like it should. But see, when you make that move right there, polynomial functions do not do that. And by that, I mean they don't make a sharp point. Okay? They are smooth. If it comes up, it's not going to abruptly stop. It's going to have a curve to it, turn around, and then come back. So they'll always be nice and smooth without any pointy edges. Okay, so continuous, nice and smooth, and then they have regions of what we call increasing and decreasing. We've talked about this before. key thing is to work left to right and just kind of state what your pencil is doing as you trace it. So I'm going to be tracing this one here, but I start at the left furthest edge. And you can see as I start to trace it, I'm going down. Okay, and so we call it decreasing in this region. And then once I get down here to the bottom, which is called a minimum, I start to go back up. And so this region would be called increasing. And we just have a series. When we start to graph these things, you're going to see we got regions where we're increasing. Starting on the left and going this way, and that's going up. I get to what's called a local maximum. Then I start to come back down. So now I'm decreasing. And then I'm going back, hit a local minimum. Then I start to go back up. And so now I'm increasing again. Okay, and so this one here, I start by going down, decreasing, then I'm going up, increasing, then I'm going down, decreasing, then I'm going up, increasing. Okay. So if you hear reference to it, hey, it's increasing here and here, you know it's going uphill. Versus if it's decreasing, you know you're coming downhill. All right, that's all you need to know to have success on your assignment. There is a little bit of bonus information after this if you want to continue on. When we start to define these polynomials, okay, this is the general formula to represent all the possible polynomials in the world. Now, normally, if we were building polynomials, we might do something like this. We'd say, hey, you could have a quadratic, like the one we've been dealing with. And if you needed something bigger, maybe a cubic equation, well, you could just add more letters. Now, if we continue this thought process, if I had one that was 26 letters long, actually it only takes 25 of them, I would go ax to the 25th. My next one would be bx to the 24th, going down in order, then cx to the 23rd, all the way down to z. But that would be as far as I could make it because this is going to have a total of 26 terms when I get done with it. Remember, this one is x to the 0. That's that 26th term. And so I'd be limited if I used a, b, and c for my coefficients. And so in this general formula, they haven't used a, b, and c. Instead, they've used little subscripts to say, hey, the first one we'll call the coefficient a sub n. The second one will give it a unique variable, a sub n minus 1. So if your n was like 3, this one would be a sub 2. And a sub 3 is a different number, or could be a different number than a sub 2. Okay, so it's a way to give us an extended or an infinitely long polynomial. I'm no longer limited by 26 letters. Now I can have any size polynomial I want. So I'm going to build a few polynomials so you can see what the general form would look like were you to apply this little formula to it. Or this model would be a more appropriate statement. So I need to figure out how to erase big chunks of stuff quicker. Because that's not going to work if I have to take that long. So let's do this. There we go. So let's take a look at what happens here if I just want to build one that has an n value of 2. It'd look like this, f of x equals a sub 2, because that's where my n is, and it'd be an x squared up at the top. Then the next term has a sub, look, it's n minus 1, so it's 2 minus 1, and the exponents go down by 1 degree. And your last term is a sub 0, 1 minus 1. Okay, we keep just subtracting 1 from it. And x to the 0. See, that's our ax squared plus bx plus c, but it's using a sub 2 plus a sub 1 plus a sub naught. Okay, and we usually don't show this last x to the 0 power. Here's if n is 3, so now we're dealing with a cubic polynomial. And all these subscripts just go down in order, And your degree on the exponent just keeps going down by 1. And again, we wouldn't write it with all of that stuff at the end. We just write x to the first as x, and a to the 0, a sub 0 times x sub 0 is just a sub 0. And so that's what they look like. And then if you get something really, really big, n to the 12th, it looks something like this. A sub 12, x to the 12th, plus a sub 11, x to the 11th, a sub 10, x to the 10th, and it keeps going like this till you get down to a to the first times x plus a sub 0. And so there it is, expanded or written out with a 12th degree using this as my model. Okay, you'll notice this thing would have 13 terms in it. It's got 12 when you get down to here, and then you have to have that extra one to give you a total of 13. Okay, so there's some bonus stuff to see how to use that general polynomial form.